Well, welcome back, everyone. This is Mrs. Hanson, picking up with our lessons in Chapter 1, Section 4. We now turn our attention to measurement, a very critical aspect of chemistry to ensure accuracy and precision throughout our experimentation. So let's stress the importance of every measurement being composed of not only a number, but also composed of a unit. And you're going to hear me stress every single time we're working out a problem or reporting lab data or so forth, that every number must also include a unit to give it meaning. Without that ever important unit, that number is simply meaningless. Here are some examples to kind of tie into our health professions and just everyday lives. For example, a proper dosage of aspirin. Would it make sense to say 325 milligrams or 325 pounds? So you can clearly see with this example, milligrams makes much more sense in proper dosage of an aspirin compared to the term pounds. It's much too large. How about if you're running a 100-meter dash? Would you be fast if you were running that 100-meter dash in 10 seconds or in 10 days? So clearly we can see that seconds is the best unit for a fast time. Here's a brand new baby being measured, and you can see the length 21 inches or 53.3 centimeters. Those are equivalent values, one in the English and one in the metric system. Every number must have a unit. And the mass of this new little infant, 8 pounds, 8 ounces, or 3.9 kilograms. Every number must have a unit. And as we begin exploring the metric system, this is the scientific unit of measurement used worldwide. It is what we will use in every science class here at Western, and every science class across America as well. The metric system is based on the unit 10. Each type of measurement has a base unit in the metric system, and we're going to go ahead and fill in together and practice with the metric system, converting from one unit to the next. The length has a base metric unit of a meter, and it's abbreviated with a lowercase m for meter. The basic quantity of mass is measured with the unit gram, and gram is abbreviated with a lowercase g. And let me stress the importance of making sure we see that these are lowercase for mass, lowercase for grams, simply because there are other units coming later where capital M stands for the metric prefix mega. It stands for a concentration unit called molarity. It has other meanings, so we want to make sure we notice it's a lowercase m. And the lowercase g for gram, because a capital G could stand for the prefix giga in the metric system as well. So a lowercase g. Now notice something unusual here with the capital L for the volume. So that's a critical part of knowing that I need a capital letter for the volume liter. And of course a lowercase s for the term second. So we've highlighted each one of these base units, kind of making note that each one of those is a one-letter symbol for the base unit of length, mass, volume, and time. Those are the basic types of measurements we use in chemistry. Other units are related to these base units by the power of 10. Larger numbers and smaller numbers are related to the base units. We put a prefix on the unit name to indicate if the unit is larger or smaller than the base unit. We need to memorize the following symbols and their values in the metric system. So let's take a moment and fill these out together. The first is a giga, and I mentioned a moment ago that that's capitalized with a capital G for giga. Giga means a billion. That is a large number, a value of 10 with 9 zeros. So 10 raised to the 9th power represents 9 zeros after the number 1. A gigameter is 1 billion times larger than a meter. A gigaliter is 1 billion times larger than a liter. The next unit we'll look at is called mega, capital M for mega. Mega represents a million, and a million is 1 with 6 zeros after it. So in terms of scientific notation, 1 with 6 zeros is 10 to the 6th. Now also keep in mind, we could write this as 1 times 10 to the 9th, 1 times 10 to the 6th. Those are exactly the same values, simply because 1 times any number is itself. So 10 to the 9th is 1 times 10 to the 9th, represents the number billion. 1 times 10 to the 6th, or simply 10 to the 6th, represents the number 1 million. Here we notice in our next kilo prefix, kilo represents 1,000. So 1,000 has 3 zeros after it, so we write that as 10 raised to the 3rd power. And so I can see 1 times 10, oops, I don't want yellow there. 1 times 10 to the 3 is 1,000. A kilometer is 1,000 times larger than a meter. A kiloliter is 1,000 times larger than a liter. So notice that giga, mega, kilo are all larger than the base unit. And now as we approach going down further in this chart, these are all going to become smaller than the base unit. So the numbers are getting larger as you go up this way, and the numbers are going to get smaller as we go down the chart. The next prefix we'll look at is known as deci. Deci is little d. Deci represents 1/10 of the base unit. So 1/10 is written as 0.1 or 1 times 10 to the negative 1. So keep in mind as you look at that, 0.1 is 1/10 the size of the base unit. 1 times 10 to the negative 1 would be how we write that. And then comparing centi, which stands for 100th, 0.01, 1 times 10 to the negative 2. Here I have a milli, a lowercase m, milli, not to be confused with mega, which is a capital M. Here's milli, which is 1,000th the size of the base unit. A millimeter is 1,000 times smaller than a meter, 1 times 10 to the negative 3. Notice again as I proceed through the chart, I have a micro. Micro is a millionth, and a micro has kind of a funny little symbol to it. It's like a squiggly U. In the Greek letter system, it's a lowercase u, so micro. And it's millionth. Notice that it has 6 zeros in the placement, 1 times 10 to the negative 6th. And then of course, oops, we wanted that highlighted. And the last one will be a nano. And the nanometer is exactly 1 times 10 to the negative 9th, which is 1 billionth the size of the base unit. So here we've had an opportunity to kind of get our feet wet in looking at the things that we have to work to memorize, the value and the scientific notation given to each of these prefixes in the metric system. These are probably very familiar to you from just working in science classes before, and these are the metric units that we'll be practicing converting. Now on the next page of your notepad, I gave you this little visual to kind of help you understand how I can change from one unit to the next using the metric system. Notice this area here is called the bench, and I called that the base unit. So that's just simply the number 1. The base unit represents either a meter, a liter, a gram, or a second. Those are the base units. A little m for meter, capital L for liter, lowercase g for gram, and a lowercase s for second. Those are those abbreviations. So those are what we call the base units. As the numbers get larger, we talked about deca, hecto, kilo. If those are new prefixes from what was on the previous slide, we just know that every time we add or subtract a 0 on the number line, there's a prefix to represent that. So deca is 1 times 10 raised to the first power, hecto and kilo, and so forth. Here's deci, centi, and milli as we proceed down the number line. The numbers get larger as we go up the staircase, and the numbers get smaller as you go down the staircase. So you're really just deciding, as you convert from one unit to the next, how many staircase steps are between the two units. So let's do some practicing. What term is used for each of the following units? 1,000 seconds. 1,000 is very large, so if I write that out as 1,000 seconds, what we're being asked is, what prefix represents the term 1,000? So if we go back to our chart, notice that 1,000 is the prefix kilo. And so I could write this as an equivalent value, saying 1,000 seconds is the same as saying 1 kilosecond. Those are equivalent numbers. A millionth of a gram. Now this millionth is small. So when we look at the larger unit having the 1, right? So here you have 1 gram and a millionth of a gram. That's that prefix. Oops, I went too far. The millionth here is this micro. A micro represents the term millionth. So to write out a millionth of a gram, we'd have 0.000, 1, 2, 3, 4, 5, 6, and that would be grams. 1 times 10 to the negative 6 is that equivalent. And I'm just kind of giving us the definition here of the term micro. So if I wanted to, let's just say that is this way. Oh, let me erase that and make this very clear for us. It would take 1 million grams. 1, 2, 3, 4, 5. Oops, I missed a 0. 1, 2, 3, 4, 5, 6. 1 million micrograms is equivalent to 1 gram. That's what we're getting there. A millionth of a gram is simply called a microgram. So letter B, I'm just kind of going over step by step of how these come out. 0.000001 gram is the definition of a microgram. That's the amount of weight we have here with a millionth of a gram. Microgram. Notice that squiggly U for microgram. It looks like a little cursive U for the term micro. How about a million liters? What would that look like? A million liters needs a prefix for the term million, and notice that was this capital M for mega. So when I write out this value, I want a capital M megaliter, and that stands for 1 million liters, which is 1 times 10 to the 6 liters. We abbreviate that as a megaliter. 1,000th of a second. Do you have it by heart yet? 1,000th, hear the TH on there? 1,000th is known as a milli. So that's a lowercase m. 1,000th of a second is a millisecond. And I'm going to write that out so you know what they also stand for. Just good idea up here too is megaliter. And here we would have a millisecond. How about 100th of a gram? And again, as we're working to memorize, 100th has this prefix centi. Centi represents 100th of the base unit. So we would have a centigram. And let me write it out so it just as practice for what to say when we see the symbols. A centigram. And 1/10 of a liter. We see the prefix tenth as deci. That's a lowercase d. And so a deciliter would have a lowercase d and a capital L as a deciliter. Practicing again with just simple, trying to work to memorize these base units in the metric system. And you can simply check. A megaliter, we abbreviated ml. Millisecond, lowercase ms. Centigram, and a deciliter. When we measure length, we do so in a base unit known as the meter, which is a lowercase m. And notice that we have these prefixes to help us realize if the unit we're measuring in is larger or smaller than the base unit. If the base unit is a meter, we would see the prefix kilo representing 1,000 meters. A kilo means 1,000 in the metric system. A millimeter represents 1,000th of a meter. So 0.001 is a thousandth of a meter. Keep in mind 0.1 is a tenth, 0.01 is a hundredth, 0.001 is a thousandth. A millimeter is a thousandth of a meter. It would take 1,000 millimeters to equal 1 meter, as another way of thinking about those relationships. And a centimeter represents 100th of a meter. It would take 100 centimeters to be equivalent to 1 meter. Another way of thinking about those relationships. The smaller the unit, as in centi, the more zeros it has to equal the base unit. When we measure mass, measuring mass is used, and just kind of defining it, as the measure of the amount of matter in an object. And when you compare that to the term weight we know represents the amount of gravity being pulled on an object. So there we're just kind of comparing those two. Mass is a measure of the amount of matter in an object, and weight has to do with the force of gravity being pulled down. So if you're up on the moon, you have the same mass, but your weight is significantly different. It's much lighter, about 1/6 the mass, 1/6 the weight here on Earth. The base unit of mass is called the gram. The gram is abbreviated with the lowercase g. So as we kind of practice some of these, we can see the large unit of a kilo. A kilogram is 1,000 grams. It takes 1,000 grams to be equivalent to the kilogram. Here we have milli, which is 1,000th, which is a smaller unit than the base unit. So a milligram is equivalent to 0.001 grams. It would take 1,000 milligrams to be equivalent to a gram. And when we measure volume, volume is in the base unit called a liter. If we have a kiloliter, that's equivalent to 1,000 liters. If we have a milliliter, that's 1,000th of a liter. Notice another way of thinking about this would say 1,000 milliliters is equivalent to 1 liter, where the base unit is given 1 and the smaller unit, milli, represents 1,000. Sometimes we have to measure volume of an object, and if an object has a surface level that has a length, width, and height, so we call this a regularly shaped object, that you can take a ruler and actually measure the length of the length, width, and height. So if we just called this, I'll use yellow, length, width, and height, we can find the volume of that cube, if they're all the same, or volume of this rectangular object, as taking the length times width times height, and knowing that it comes out to be a centimeter cubed. And I'm going to highlight something very important, which is true for water. Since water has a density equal to 1, the value of these 3 units is exactly equivalent for the water, which has a density of 1. 1 mil is exactly the same as 1 cubic centimeter, which is exactly the same as saying cc. This is how we see cubic centimeter often abbreviated. 1 mil is the same as 1 cubic centimeter, which is 1 cc. And if it is indeed water again, that's equivalent to saying 1 gram of water as well. All of those are equivalent values. Here is a table that expresses English units and their metric equivalents in relationship form. Now I'm saying that we don't have to memorize these, but what we do have to know is how to look them up and to use them for problem solving. So when I say don't memorize, some of them you might already know, but some of them might not. I don't know every single one of these by heart. Some of them I do, but not all. And so I'm saying don't worry about memorizing the equivalents of English units and their metric equivalents, but just know that there is a table provided if we're working a story problem and we need to know a conversion factor, then look these up in this chart provided. If you're working a story problem on a test or quiz, these English units and their metric equivalents are provided within the reading, so you don't have to worry about memorizing. Notice the setup, we have some length equivalents, we have mass equivalents, and we have 4 rows of volume equivalents as we work to just kind of go through English to metric relationships. Now in the health professions, one of the most common metric conversions to English conversions is in the volume. So we'll kind of be focusing here quite a bit as well in our practices. Let's determine which quantity is larger in each pair. This again is simply practice with the metric prefixes. The first one gives us 3 milliliters. So I would say that 3 milliliters is really equal to, remember milli is a thousandth. So we would have this value of 0.003 liters. Simply remember that milli means a thousandth. So I'm just kind of expressing that in terms of what that decimal means. And then I have 3 centiliters. Centi, well, I know that centi represents a hundredth. And so if I were to write that out, a hundredth would have this particular look. And when I write those out in decimal form, it's easier for us to see which one is the larger unit. Is a hundredth larger than a thousandth? And the answer is yes, absolutely. So a centiliter is larger than a milliliter. The next one gives us nanogram, and that prefix nano represents a billionth. And the prefix microgram, nano versus micro, that's another good thing to write. Nano, billionth, and micro, well, that means that it is a millionth. So we have micro representing a millionth of a gram. So here, looking at the value, is a billionth or a millionth the larger value? Well, 1 times 10 to the negative 9 versus 1 times 10 to the negative 6. A millionth is a larger value than a billionth of a base unit gram. And number 3, a kilometer, which would be, kilo means 1,000, so this would be 5,000 meters for a kilometer. And then a centimeter, so a centi is a hundredth, so you would have 0.05 meters being equivalent to 5 centimeters. Clearly we see 5 kilometers as being a much larger number. 5,000 is much larger than 0.05. And the last one, 2 millis or 2 microliters. Of course, a milliliter is a thousandth of a liter, and a micro is a millionth of a liter. So milli, which represents a thousandth, and a micro, which is a millionth. The larger unit is a milli. And we highlighted those correctly, didn't we? The larger unit, a centiliter, a microgram, a kilometer, and a milliliter. And we're working these practices to help us get proficient in memorizing the values of those particular prefixes. In our next lesson on significant figures, this takes us into a journey of recognizing how many decimal places we need to report as we begin kind of going through our measurement values. So not only is it important to include a unit on every number, it's critically important to include the right number of unit values in our calculations, in the numbers that we report in our measurements. Let's begin by comparing what an exact number versus an inexact number represent. The first term is called an exact number, and it results from counting objects or part of a definition. There is no vagueness to the number at all. For example, I have 10 fingers. It's not about 10. I have 10 digits on my hands. I have 10 toes. I found those by counting. Part of the definition of the term centi represents its value as being 1/100th of a meter. So it would take 100 centimeters to be equivalent to 1 meter. That's part of its definition. It's not about 100, it's exactly 100 centimeters in a meter. Anytime we measure something, whatever instrument we use to measure has a degree of uncertainty, and therefore it's termed as an inexact number. If I'm using a ruler to measure the length of a page, the ruler has a certain certainty in its, in its actual precision. I have 15.3 centimeters when I measured the length of a page. I have 1,000.8 grams sitting on the scale. I measured 0.0034 milliliters in a graduated cylinder. Anytime I'm using a measurement, I have a degree of uncertainty based on the piece of equipment that I was given. How accurate is that instrument? Since it's being measured, it is not considered an exact number, but rather an inexact number. If I have a container of 71 macadamia nuts and it weighs 125 grams, the number of nuts is exact because I sat there and counted out how many nuts were in that container. It's not about 71, it is exactly 71 based on counting. But when I used a scale to take the mass of the nuts, I'm using an instrument that is limited to a degree of precision. The degree of precision makes it an inexact number. 125 grams is an inexact due to measuring. Notice here I'm taking the length of a fish. Suppose the meter stick or centimeter ruler that I'm using has base units of just whole number centimeters. The tip of the fish between tail to head gives me an estimation of about 53 centimeters. I have to estimate how many ticks over past 50 I'm at. So the last number that was on the ruler stick was 50 centimeters, and I've estimated how far past I'm measuring. So I'm putting 53 centimeters down. If I'm using a ruler stick that has little tick marks between the 50 and 60, I now can count over with certainty here 3 marks to get 53, but it's lying between 53 and 54. So I have to estimate where it lies between. So I'm going to estimate that it's lying halfway between the 53 and 54 tick mark. So I put in 53.5 as the estimated digit. When we're reporting measurements, I don't care if it's a scale, a ruler, a graduated cylinder, whatever the instrument is that we're using to take a measurement, the term significant figures plays a role. All are digits in a measured number, including one estimated digit. So you are to report all measurements through what your instrument is telling you. For instance, this is telling me 53, 1, 2, 3 over, but I'm going to include 1 past the degree of the instrument's precision in terms of an estimation. If my instrument had whole numbers, I was able to put in the 53 as the estimation. If my ruler stick here is giving me decimal points or units after the 50, I'm going to estimate 1 unit past the degree from the instrument. The term significant figures is what we're discussing. These significant figures are all the digits in a measured number, including 1 estimated digit. We're going to review how to determine if a number is indeed significant. First, all non-zero digits are always, always, always significant. If I see a number 65.2 grams, notice I have a number and it's essential to include a unit. All of these numbers are non-zeros, so this number contains 3 significant figures. 255.345 grams, all are non-zero numbers. They are all significant. That number contains 6 sig figs. It's the zeros that require practice. Let's talk about the zeros and determining whether or not the zeros are indeed significant numbers. A zero counts as significant when it's between 2 non-zero numbers. So that's critical. Here's a 0 found between, let me change color. Here's a 0 found between non-zero digits, automatically counted as significant. 29.05 has 4 sig figs. Here are zeros found between non-zero numbers. That means they're automatically significant. That's 5 sig figs. If the number has a decimal place in the value, at the end of the number, anytime you see a decimal place, the zeros will be significant. Notice the decimal place is placed in this 3.7500. That tells me that these are indeed significant zeros. Here's a decimal point at the end of the number. That will automatically make 0 a significant digit. Zeros between non-zero digits are always significant. Zeros at the end of a number that contain a decimal place are always significant. Let's talk about when zeros are not significant. A 0 does not count as a significant figure when it occurs at the beginning of a number and is really just being used as a placeholder. For example, 0.00. Those 3 zeros are not significant because they are not between 2 non-zero numbers, and they're just there to be a placeholder to let you know that this is 0.00245 milligrams. Notice here again, these zeros are not significant because they are occurring at the beginning of a number. There is no non-zero number prior to them, and they are just being used as placeholders. The second time a 0 does not count is when they're at the end of a number that does not have a decimal point. For example, 2570 has no decimal point, therefore the 0 is not significant. 1245500 has no decimal point at the end, therefore those zeros are not significant. A 0 is not significant if it starts the number with no other non-zero number prior. If it's at the beginning of a number, it does not have a different number in front of it, it is not significant. And again, if it's at the end of a number with no decimal point, it is not significant. Recognizing when zeros are significant or not takes practice. So let's try one. How many sig figs in the value 0.003450120? Our rules say that any zero that starts a number and is just there to use as a placeholder are not significant. Any zeros that are after non-zero numbers are indeed significant if the value has a decimal point. So in this example, these 3 zeros are not significant figures. I have 1, 2, 3, 4, 5, 6, 7 sig figs. Here we have an example where we have 34.08. 34.08 has a 0, but it's between two non-zero values. Therefore, all numbers are significant. In our next example, we have 0.00054. Those zeros are placeholders and are therefore not significant. In the next example, we have 260.00. This is a number that has a decimal point. Therefore, all zeros are indeed significant. 1, 2, 3, 4, 5, 5 sig figs. And the last one, 260. This has no decimal point. Therefore, this is not significant. Therefore, we have 2 sig figs. Here we've highlighted our answers. 34.08 does indeed contain 4 significant figures. 0.0054, only the last 2 are significant. Number 3, because there is a decimal point, all 5 digits are significant. And number 4, because it lacks a decimal point, only the first 2 digits are significant. Try some more on your own. How many sig figs does each number contain? Try them, pause the video, don't cheat yourself, pause the video, come back when ready to check your work. All right, well, welcome back. You must be ready to check. Let's share and see how you did. In the first example, all digits are significant. There are no zeros to even worry about, so there's 4 sig figs in problem 1. In the next example, letter B, 23.057. Since there is a decimal point, the 0 is between 2 non-zero digits. All 5 digits are significant. In number 3, there is no decimal point. 230 only contains 2 sig figs. The lack of a decimal point makes that 0 insignificant. Number 4 does contain the decimal point, so all 4 digits are significant. Number 5, the placeholder 0 prior to the decimal is not significant, only 3. Question 6, the placeholder zeros are not significant, only 3 sig figs. Question 7, the zeros lie between 2 non-zero numbers. They are all significant. Question 8 lacks a decimal point. Therefore, There are only 2 significant digits. Number 9 also lacks the decimal point. Therefore, only 4 sig figs. And number 10 does have the decimal point. And because it has the decimal point, this is a significant digit at the end, giving us 5 significant figures. I'm proud of you. You're working hard. Well, let's talk about adding and subtracting, multiplying and dividing, and figuring out how many sig figs we should report in our final answer. And there's rules that relate to multiplying and dividing, and those rules are different from adding and subtracting. So let's focus first on multiplying and dividing and applying the rule to significant figures reporting. So the rule says our answer has to have the same number of significant figures as the original number within the question that had the fewest sig figs. So I'm only allowed to report in my final answer the same number of sig figs as the fewest given to me in the problem. Here's an example. If I take my calculator and divide the following, 351.2 miles, which has 4 sig figs, the 3, 5, 1, and 2 are all significant figures, and I hit divide by 5.5, which has 2 sig figs. My calculator screen has a big old number on it. The calculator doesn't apply the rules of significant digits. The calculator screen reads 63.854545, and probably will continue that chain for a long time, depending on how many decimals you have on your calculator screen. Just to kind of verify, if we were to hit 351.2 and we divide that by 5.5 and hit equal, notice we get a very long answer on our calculator screen. How many decimals, how many sig figs are we allowed to answer with? And the rule comes from having the same number of sig figs as the fewest in the problem. Notice the time only had 2 significant figures. So that means I have to round this to only have 2 sig figs in the final answer. The question becomes, how do I round 63.854545, and that just continues on the screen for a long time, only being allowed to report 2 sig figs. So let's just talk about how we are going to round. If the first digit to be dropped is between 0 and 4, drop it and all the remaining digits. Now let's just focus on what that's saying. We're only allowed 2 sig figs. So that means this 8 is the first digit we have to drop. If that number is between 0 and 4, just drop it. But if the number is between 5 and 9, you're going to round up the last digit to be retained by adding 1. Just round it up by adding 1. So the digit we're rounding is an 8. That's between 0 and 5. So we're going to add 1 to the 63, and the final answer becomes 64, rounding up to the next whole number, 64 miles per hour. That gives us our required 2 sig figs in the final answer, which is kind of, disturbing to some students, saying, look, we had 1 decimal point in each of these. Why aren't I allowed to report with 1 decimal point? Well, that's not the rule for multiplying and dividing. We have to remember that. Only report the same number of sig figs regardless of decimal. In this case, it was 2 sig figs, so the final answer, 64 miles per hour. Remember, as we're rounding, it just really is a practice of figuring out how many decimals to carry, trying to figure out how many places to put into there. And this really is just a little help, a little grid here to figure out rounding. And just nothing to write here, but let's just kind of think this through. If I have a final number of 61.2537. And notice that's the same number going down. And I'm only rounding to 2 places. I'm going to look for the first digit to be dropped as the number 2. Since it's below 5, we're just going to drop it and say it's 61. If I have to report to 3 places, 5 is the first number I have to drop. So I'm going to round up 61.3. If I have to report to 4 places, the 3 is the first number that's going to be dropped. Since it's below 5, I simply drop it, 61.25. And if I have to report 5 sig figs, 7 becomes the number to be dropped. Therefore, you can see that we rounded up. So that's just practice with what I'm referring to as rounding. Round off each number to 3 significant digits. 3 sig figs. So the first number that I need to drop in part 1 is the number 3. So if I drop that, 3 is not going to be rounded up. 1.27 is just this value. And I know that these are not measurements, so there's no units there. It's kind of upsetting that there's not a unit, but we're just practicing rounding. 1.27 is 3 sig figs. Here we have 1, 2, 3 sig figs. This is the number that we need to look at. It's the number that will be dropped. Clearly it's above 5, so we have to round up. So we go 0.00. Those are not significant digits. Then I go 2, 5, rounding the 3 up to a 4. That's 3 sig figs rounded up. And here's a large number, 1, 2, 3 sig figs. So this is the number I have to drop. Keep in mind we need the magnitude of the number to stay the same. We still need it to be 3,800. 6 is going to round up, so we have 40, no decimal, so that the 0 does not become significant. 3,840 is rounded up to 3 sig figs, and the magnitude of the number, how large it is, has been retained. And that was our answer, checking through there. Let's carry out each calculation and answer using the proper number of significant figures. We're practicing the multiplying and dividing rule. Number 1 gives us 3.81 times 0.046. On our calculator, we're going to hit, let's just clear this screen, 3.81 times 0.046, and then we'll hit equal. We get 0.17526. How many sig figs are we allowed to report? The first gives us 3 sig figs. The second gives us 2 sig figs. We're only allowed to report our answer with the fewest number, which is the number 2. That means this is the number that I have to drop to report only 2 significant digits. That number is a 5, so we must round up. That's going to be rounded to 18. Let's try number 2. 120.085 divided by 106. 120.085 divided by 106. And I get a number, 1.32877. I'm not going to bother writing all those decimals. I'm just going to carry a few that I can remember in my head. 1.1328, 1.1328, 1.1328. That's plenty. Now, what do we need to do to round that properly? This value has 1, 2, 3, 4, 5, 6 digits that are significant. This value has 3 digits that are significant. The 0 is between non-zero numbers, so it is indeed significant. My final answer can only be reported with 3 sig figs. 1.13 will be my final answer. The number that I'm going to drop begins with a 2, so I do not round up. The answer is 1.13. How about if you try these with your calculator and come back when you're ready to check your answers? Pause the video. Please don't cheat yourself. This is where the learning deepens, especially as an online learner. Welcome back. You must be ready to check. 10.70 times 3.5, we are only reporting 2 significant figures, so the value becomes 37. 0.206 divided by 25.993. I'm going to hit that on our calculator. 0.206, whoops, I missed that. 0.206 divided by 25.993. That has 1, 2, 3, 4, 5 zeros as placeholders. 79252. 79252. This is not right. Hi, question number 2. So if you notice, I just paused the video and came back to check that calculation. That's not a correct answer. I'm going to hit again 0.206 on my calculator and divide it by 25.993. And what my screen says is 7.9252, that's plenty, times 10 to the negative 6th, and which is 0.00000799252. Those are the same number. One is expressed in scientific notation, one is in standard notation. We're only allowed 3 significant digits, which is this number here being rounded. So our final answer, 1, 2, 3, 4, 5, 7, 9, 3, which is 7.93 times 10 to the negative 6. You may certainly report those in either way. This is known as standard notation. This is known as scientific notation. The third, we're reporting only 2 sig figs, so we report it as 32. And number 4, we're only allowed 2 sig figs, so 3100. $120.5 times 26. The answer came out 3133. Since we're only allowed to report 2 sig figs, we drop these. No decimal. We don't want those zeros to be significant, so no decimal point there. 1300 divided by 41.2. That's where your screen said 31.553. So therefore only 2 sig figs allowed. This number made us round up to the 32. I talked about B. 10.7 times 3.5. Your calculator said 37.45. Only 2 sig figs. This number 4 will be the first that we drop, so therefore no rounding took place. How'd you do? A couple more practices and I'm sure you'll have it. Now that we've practiced multiplying and dividing, let's talk about adding and subtracting. The rules are a little different. The answer has to have the same number of decimal places as the original number with the fewest decimal places. So notice here the distinction is we are not counting total number of sig figs as we did with multiplying and dividing. Instead, we're looking at adding and subtracting and counting decimal places. For instance, 10.11 kilograms has 2 decimal places. Minus 3.6 kilograms has just 1 decimal place. When I subtract, my calculator would read 6.51 kilograms. The calculator doesn't apply the rules of sig figs. We need to do that. Knowing that we can only report the fewest number of decimals, which was 1 from our problem. The first number we have to drop is a 1, so clearly we won't round. This simply becomes 6.5 kilograms. Let's practice another together, kind of talk out loud. We have a woman on a diet, how appropriate for the new year. A woman lost 3.52 pounds the first week, 2.2 pounds the second week, and 0.59 pounds the third week. How many pounds did she lose in all? So we're adding those values together. If we add 3.52 plus 2.2 plus 0.59. So that's all I've done. I used my calculator, but I can share with you what I'm hitting there. It just was 3.52 plus 2.2 plus 0.59. And the calculator reads 6.31 and then a whole lot of zeros. So 6.31 pounds. Now, how are we to report that using the proper number of sig figs? I go back into my problem and I find the number that has the fewest decimal points given to me, which was the 2.2 pounds. That means I can only report the 1 decimal point and I must get rid of everything past that. So I'm going to have to get rid of the 1. I wouldn't round it, so this simply becomes 6.3 pounds. Since we have just 1 significant decimal, that's where we end with 6.3 pounds. Let's add the following and see what values we come up with. We're going to practice carrying out and see what we find. On my calculator, I'll hit 27.8 and I'll add to it 0.246. So you're doing the same thing. Let me stress what we're hitting. 27.8 plus 0.246. I'm just adding those two values together and I get 28.046. Now, how many decimals are we allowed to report? The first number has only 1 decimal place. That means I'm only allowed to report 1 decimal place. I look at the next number and decide if I should round up. 4 does not get rounded up, so I will report 28.0 centimeters as my final answer. Let me hit 102.66 plus 0.857 plus 24.0. When you hit that on your calculator, you get the following value: 102.66 plus 0.857 plus 24.0. And your screen reads like mine, 127.517. Now, how many decimals are we allowed to report? The first one gives us 2 decimals. Here we have 3 decimals. Here we have just 1. I'm only allowed to report the answer with the fewest number of decimals, which is just 1. That means the first number I'm going to have to drop is the 1. We don't round that up, so it's just 127.5 mLs. 54.6 minus 25. My calculator reads 29.6. We're not allowed to report any decimals. 25 has no decimals, so we need to get rid of our decimal. When I round up 29.6, I get 30. Now keep in mind, I need 2 sig figs there, so I'm just going to put the decimal point so that you know that 0 is significant. I don't write 0.0, or that'd be, I have to have no decimals in my answer. So 30 point and stop. And then the last one, 2.35 minus 0.266. My screen reads 2.084. Oh, I should have put milligram there, sorry. Let's see, we're allowed only 2 decimals. The 2 decimals, I would have to drop the 4, no rounding with that, and we get 2.08 seconds. Are we getting the hang of it? What do you think? Well, I'm so super proud of you for working so hard with us. I'm going to pause our lessons now. When you're ready to come back with your next lesson, we'll talk about scientific notation. We're getting there, gang. Lots of hard work in our first chapter for sure.